There is another very useful measure in statistics which helps us evaluate the variation in a series with respect to its mean. And also then this helps us compare the variability across two different data set or data series. So this measure is called the coefficient of variation and is essentially given by just looking at the standard deviation of a series, dividing it by its mean, and then multiplying by 100. So a series with a higher number has more variability relative to its mean. So mean is kind of scaling it. It's kind of looking at standard deviation, but then standard deviation by itself is a hard concept because it can be a big number or a small number. We do not know what that number means. We can look at standard deviation relative to its own mean, and then that ratio tells us the extent of variation compared to the mean. So a series with a higher number shows more variability with reference to this mean. We will use this idea kind of in the z-scores as well. So the next concept of variability is the z-score. So we've all seen bell-shaped curves. What z-score is doing is it basically standardizes the data. It looks at a data, finds its mean, its standard deviation, subtracts the mean from the data point, and then divides by the standard deviation. So if we examine this closely, it is just telling us how far is a data point away from its mean in terms of its standard deviation. So the z-score is essentially telling us the spread relative to the standard deviation, to the mean, how far is the data in terms of standard deviation. And then this helps us also easily identify outliers. The empirical rule of normal distribution, which is bell-shaped curve, is that 99.7% of the observations lie within 3 standard deviations of the mean. So once we convert a series into its own raw standard deviation away from its own mean, any number more than 3 or less than -3 would be considered an outlier because it would be beyond 99.7% of the values that might be in that data set. So again, a very quick way. So if z-score can be a little confusing, just know that what we're doing is we are basically transforming a data point in how many standard deviations away from the mean, from its own mean, that data point is. So one measure of outliers was the z-score, anything above or below absolute value of 3. And then an alternative approach, which we will again see in the chart that we just had a little while ago, is that we can look at the difference between our first and the third quartile, the IQR range. That gives us kind of limits to the outliers in terms of the percentiles. So the lower limit for an outlier is our first quartile minus 1.5 times the interquartile range. And then the upper limit is a third quartile, which is 75th percentile, plus 1.5 times the interquartile range. Anything above or below these limits would be considered an outlier. So let's see how we can assess outlier with these measures. Here is our series on market cap that we had looked at. And we had already obtained the histogram for the market cap series. And then we noticed that Jump always produces this curve on top. We had not discussed it so far. This is called the box and Whisker plot. So the boxes are essentially the values of the first and the third quartile. So the lower end of the box is our 25th percentile, which is 122.5. And if I hover our mouse here, we can see that being called out as well. And then the top end of the box is a third quartile, which is the 75th percentile. Then the whiskers are on either side the highest and the lowest value in the data, which is not an outlier, as given by our IQR measure. So IQR plus 1.5, sorry, Q3 plus 1.5 times IQR. Anything less than that, but as the highest value in the data set, would be where this whisker is. Similarly, this whisker would be Q1 minus 1.5 times IQR. If the value lies between that. The smallest value permissible in that range would be this lower whisker. And then these two dots, these are the outliers. So box and whisker plot provides us with kind of the 5 values. It provides us with the first quartile, which is right here, the third quartile, the the median, and then also when this line in between these two triangles, that's the mean. So we see that the mean is much higher than the median, which is over here. And then we saw that with our raw data as well. Our mean was 425 and our median is 210. So this line is the median, but then the middle of this rhombus is the mean. And then another advantage of box and whisker plots is that any outliers then come out as individual data points. And we know that this one is Microsoft and this is Apple. So very quickly we can assess the outliers. And then the other concept we had talked about was the coefficient of variation, which is essentially the standard deviation divided by mean times 100. We can calculate it by hand, or we can also request that in JMP. We can customize summary stats. There should be an option coefficient of variation as well, CV, which is the coefficient of variation. And we click OK. So this tells us the coefficient of variation, that our standard deviation, which is 715, divided by our mean, which is 425 times 100, is 168.2297. This shows a very high level of variability again, because by construction, mean and the variances are affected by the outliers. To look at the z-score, we will basically take each of these values, subtract them by the mean, and divide them by the standard deviation. So we'll take 102 minus 425 divided by 715, and we keep doing that for every single data point. But in JMP, we can very easily obtain standardized values. We right-click on the column, then we click on New Formula Column, and this is a distributional. So we have a bunch of options: statistical, transform the data, doing a log. Distributional option is standardized. So standardized is essentially taking the z-score. So we click here, and we obtain the z-scores for each of these market cap values. Again, as we said, anything above or below 3 absolute value would be an outlier. And unsurprisingly, Apple's value is 3.53, which is way outside. So we would consider that as an outlier. And so is the Microsoft. Actually, not because Apple is so extreme. It is z-score is 2.98. But again, if we look at the outliers in terms of the box and whisker plots, both of these companies stand as an outlier. So we see that sometimes there may be a difference in agreement between what an outlier is if you look at the z-score versus an outlier if we look at the box and whisker plot. And again, the context tells us which measure to go with. So far, we have looked at only individual series separately. But quite often we're interested in finding out the relationship or the association between two different series. So the measure for that is covariance. Covariance tells us the movement of the variables, whether these variables move together in a positive way or in a negative way. An often used measure of association between two variables, or linear association between two variables, is called the correlation coefficient, or Pearson's correlation coefficient. It is essentially the covariance between x and y divided by the standard deviation of x times standard deviation of y. So it is looking at the covariance, but then scaling it by the individual products of the two standard deviations. And a higher value, so this value ranges from -1 to +1. With 0 being there's no association between the two series, +1 being a perfect positive association, and -1 being a perfect negative association between these two data series. So let's now empirically obtain these two measures. Let's study the association between market cap and our revenue for these companies that we have data for. Now, there are a couple of ways in JMP to obtain variance-covariance, but we'll look at a more general method. But notice that because we're looking at association between two different data series, in the analyzed platform, the distribution method by itself will not work because this method is looking at individual series in isolation without looking at its connections with other series. So one method to get association between two different, or in this case, any number of series, is to go to the Analyze platform, and then we'll click on the multivariate methods. And here we'll click on multivariate. And we'll drag our two measures to our Y. We're looking at our market cap, and we're looking at fiscal revenue. And here we, by default, get the correlation matrix. So this is showing that the correlation between market cap and fiscal year revenue is 0.529. Not very strong, but it's like a moderate correlation. And this gives us a scatter chart, which is just plotting the two series one against the other. So on the x-axis here we have fiscal year revenue. On the y-axis here we have the market cap. Now, how did we get this 0.5295, the correlation? We can go to multivariate red triangle or the menu button and then click on Variance-Covariance matrix. So this matrix gives us the variances and the covariances of these series. So the diagonal elements are the variances individually. So this is the variance of market cap, and this element is the variance of fiscal year revenue. And the off-diagonal elements are the covariances. So remember we said the correlation coefficient is given by the covariance of x and y divided by the standard deviation of x and the standard deviation of y. So it would be this number divided by the square root of this number as well as this number. And this is what our 0.5295 is. So this kind of shows us the association between any two variables. And this is a general method. If we had 5 or 6 or 7 or 8, how many variables, we could just get a correlation matrix. And then we could also look at the variance-covariance matrix, which would look at the variances and the covariances between the entire 8 or 10 variables. So it's a pretty general method that ways.